Okay. Alors, si ça vous dérange pas, je vais me présenter en anglais parce que je suis un peu plus à l'aise que je suis en anglais. Okay, so hello everyone. So just to present myself, my name is Alain Uwadukunze, and I'm a first year PhD student at ISL. PhD which started this year in February, and in collaboration with the University of Lorraine, and more particularly the laboratory Caen, as well as the laboratory Nanterre of the Correspond de Lyon. So artificial intelligence nowadays is being applied in many thematics, and at ISL we're trying to develop new tools which are based on machine learning techniques in order to improve the ones that we already have or to work with them. So the topic of my presentation today is artificial intelligence techniques applied to aerodynamics and ballistics. So for this presentation, I'll be talking about two main subjects. The first one is entitled Prediction of Experimental Conditions using Machine Learning, which is a small study that I did during my internship last year at ISL. And the second one is Artificial Intelligence Techniques Applied to Aerodynamics, which is basically an introduction to my PhD subject. So first of all, what is ISL? So ISL is a French-German research institute, which is based in the Saint-Louis, which is in Alsace, near Swiss and Bâle. So it hires over 200 scientists which work in thematics related to defense and security. These thematics are divided into different divisions. Maybe I'll first go here. See also. So these thematics are divided into different divisions, and the one I'm working in is called the flight techniques for projectiles. And this division is also divided into multiple groups, and more particularly the one called aerodynamic and external ballistics, which is the division I'm working in. So let's begin with the first part, which is entitled Prediction of some experimental conditions using machine learning. And first of all, let's talk about the context of this study. So the group of Albisser does a lot of experimental campaigns which correspond to the firing of different types of projectiles, as you can see here, or different types of space probes, as the one is flying here, using different types of launchers and powders. The main goal of these experimental campaigns is to do what we call aerodynamic characterizations from pre-flight data. So during these experiments, many measurements are made of either velocities, acceleration, pressures, thanks to different measurement techniques which are present on the field. For example, here you have a radar which will measure your velocity, a trajectory tracker which will follow your projectile during the flight. Yeah. So in total, we have over 2,100 samples to try out, which have been done since the beginning of something like that. So in order to have a smooth running of these experiments, some experimental values have to be predicted, which are the initial velocity, the pressure, and the mass of powder. And in order to predict these initial values, you need to read the functions, in our case, which are static functions, which will predict these values depending on some input parameters, which will not have any difference in these values. So for this presentation, I'll be talking about only two launchers, which are called 91 100 and the 105 S33. And for these two launchers, the parameters or the experimental values which are studied are the following. First of all, the initial velocity, which I will write V0 here. So the initial velocity is used to initialize what we call a trajectory tracker. So here, the objective is to...
Alain, j'ai un autre commentaire de Guillaume. Est-ce que tu peux parler plus fort? C'est vrai que...
Il n'y a pas de souci.
Ou alors tu parles un peu plus dans le micro.
Oui, il n'y a pas de souci. So the objective of the initial velocity is to initialize what we call the trajectory tracker, which we call the projectile during its flight. So here we read a static function which takes as the input the accelerated mass of the projectile. So basically the mass of the projectile, which I write mAc here, and the quantity of powder m powder, which I write m powder here, and which predicts the initial velocity. The second experimental value is the chamber pressure, which is important to know because each launcher has a maximum chamber to not exceed for security reasons, and which can also help estimate the maximum acceleration inside the launcher. So here we build a static function also, which takes as input the accelerated mass of the projectile, the quantity of powder, and which will predict the chamber pressure. And finally, we have another model which will predict the quantity of powder, in this case, which is needed to reach a desired initial velocity for a given accelerated mass. So there are other tools to do that, which already existed before my internship, and they are what we call interior ballistic softwares, which are called in-bar predictions and AMI simulations, and softwares which are based more on thermodynamic equations and a few experimental data, and which can help predict these quantities. So now let's move on to the data processing that I used. So for this case, for the 91 launcher, we had about 300 samples, and for the 105 launcher, we had about half of 300. Then before building our models, we had to do a few processing phases on the data. And the first thing that we did was to remove observations with missing values, which was due, for example, to sensors force, for example, the initial velocity that didn't measure the velocity. The second thing that we did was to add visual data which is related to prior knowledge. For example, in this case, we consider that if the quantity of powder is equal to 0, then your output of initial velocity or pressures or accelerations will also be equal to 0. So we add data that respect this criteria. And then we standardize our data or normalize it. In this case, for example, with the mean of 0 and the standard deviation of 1. And finally, we make some split our data depending on the validation method that we use. So here we have an example, for example, of our split into training and test data. So here you can see where on the board, but we have our training data in black and test data in purple. You can see that both the training and test data cover the possible range of variations of our data. So now let's move on to the model identification phase. So here represented our data of initial velocity and chamber pressure based on the accelerated mass of the projectile and quantity of powder. And the criteria that we had here in order to choose the algorithm to use or the model to use was that we needed a function that can, a method that can deal with non-linear function, because as you can see, our data here can be simply represented by a linear function. So here we have different possibilities. First of all, more classical methods like polynomial regression and more machine learning methods which are non-parametric, like for example, support vector regression, Gaussian process regression, a neural network, or a multi-layer perceptron. And in our cases, we didn't know the exact form that the model needed to have. We used a non-parametric model in order to have more flexibility on our output data. And in particular, we used a kernel-based method, which is called Kernel Ridge Regression, which I will present. Just a small precision, I use a tool which calls Python and the machine learning library, which is called scikit-learn, which has already implemented most of these algorithms. So to talk about kernel regression, so the idea behind this method is that it is the least square method for linear regression, which is regularized, with which you obtain what you call ridge regression. But ridge regression only estimates linear functions, but in order to estimate non-linear functions, we apply what we call the kernel trick in machine learning, with which you obtain kernel ridge regression. So the idea here, or the goal, is to obtain this function f that will minimize your sum of squared errors between your predicted and real values, plus a regularization term lambda, which is applied on the norm of f. So in our case here, if you consider that H is what we call a reproducing kernel Hilbert space, so by not going into too much detail, a Hilbert space is defined as a vector space with an inner product, and the reproducing kernel Hilbert space is a Hilbert space with which is associated to a kernel function. So if f here belongs to what we call the RKHS, then there's a theorem which is called the representative theorem that states that the solution of this problem is of this form, with alpha I a parameter vector with as many parameters as many samples as there are training samples, and k your a kernel function. So yeah, by knowing this, you can represent, you can put this in your first function here, and you obtain the following minimization problem, where you have to find this alpha parameter vector, which will minimize all of this. So here you have your norm f, which is written like this, when your f belongs to RKHS. So here I won't go develop again the details, but the solution to this problem is the following here, with the lambda, your regularization term, I in that matrix, and y your output. So here, for example, if you choose to use a polynomial kernel, then your function will look something like this. If you choose to use, for example, a Gaussian kernel, your function will look like this. And objective, the idea behind this kernel ridge regression method is to find a kernel that will fit the best your data. So here I'll be presenting my results with two evaluation factors, which are the root mean squared error and the mean absolute error, so which are calculated like this. The validation step is the step in machine learning where you judge a model good enough based on some parameters, with some hyperparameters. And there are two main methods which are used depending on the quantity of data that you have. In the case where you consider that you have enough quantity of data, then you divide your data into training, validation, and test-based with these foreign percentages, for example, and you do the training with the set of training with the set of parameter pi. So in our case here, the parameters that we modify, for example, would be like the regression term, the kernel you use, the degree of the polynomial kernel if you use a polynomial kernel. Then you do the evaluation on a validation base. And if the score you get on the validation base isn't satisfying, then you redo the training with another set of parameter pi until you obtain a good enough score on your validation base, with which you do the test on the test base and obtain the score of your model. In the case where you don't have enough quantity of data, where you divide your data into training and test base, with this percentage, for example, and you use a method that's called the cross-validation. So cross-validation consists into dividing your data into different subsets, and each subset is used as a validation set and the others as training sets. You do the training on the training set and the validation on the validation set, and at each iteration of this method, you change the validation set, and you also calculate the score. And the score of this method is the mean score of all the iterations. So here you also verify if the parameters you have a satisfying score or not. And if you don't, you do the training in a set of parameter pi. And when you obtain the satisfying score, you do the test on the test base and obtain the score of the model. So in my case here, I used the cross-validation method in order to train my Kernel Ridge Regression model by modifying different kernels, different lambdas here. And I also use a method called withaerodynamic, which will basically test different combination of your parameters to see which one gives the best score on your validation set. So now let's move on to the results of this first part. So first of all, the predictions of the initial velocity based on the accelerated mass of the projectile and the quantity of powder. So here in this column, you have the results for the 91 launcher, and this one you have the results for the 105 launcher. So you have the RMCs here and the MIAs here. So here the percentages represent what the RMC or the mean value represent according to the mean values in your test values. So here, for example, for the 91 launcher, we obtained an RMC of 16 and the MIA of 13 on the test base, which represent about 1.6% to 2% of your mean values. For the 105 launcher, you have the results are a bit higher, so 22 of MIA and 28 of RMC, which represent about 2 to 3% of your values. Then you have the function which predicted the chamber pressure. So for these values, you have results which are a bit higher than the 91 launcher. So you have RMC of 15 bars, and 21 bars, and MIA of 15 bars. For the 91 launcher, represent about 5 to 7% of your mean values. And for the 105 launcher, you have an RMC of 76 and MIA of 52, which represent about 6 to 10%. Then finally, you have your function, which predicts the quantity of powder. And in this case, you have an RMC of 16 to 20, which represent about 2 to 3% of the mean values. And for the 105 launcher, you have about 29 and 36, which represent about 3% of the mean values. So with these models here, the goal is to be able to predict experiments which have never been done. So which means for higher values or lower values of either accelerated masses, quantity of powder, or initial velocities. So here I plotted the results to see what they look like. So here you have different curves which correspond to different values of accelerated mass for different values of initial velocities. So as you can see here, the model looks like a polynomial because it was a polynomial kernel which gave the best results. So probably by using maybe a polynomial regression to have worked perfectly well as well. And here you have the model which predicts the chamber pressure. And what's interesting to see here is the application. As I said, each launcher has maximum chamber pressure to not exceed. In this case, it is represented by this red line. So if, for example, with this model, you can estimate at which point, so which means at which value of accelerated mass and quantity of powder you will reach the maximum chamber pressure not exceed, for example, here. So as I said in introduction as well, it is possible to do this, to predict these quantities by using other tools, such as InBal, which is an interior ballistic software. So here what I did was compare the predictions which were made by the Kernel Ridge model compared to the predictions which have already been made by IGBA predictions. And I compared them to the real values which were obtained with the experiments. So here I presented the proximity to real values. As you can see here, for the initial velocity, you have about the same percentages or the same predictions for interval and the machine learning predictions. But for the chamber pressure, you have much better predictions for the machine learning model than for the interval predictions. But this can be also due to the fact that your machine learning model learned these values, because I'm not sure if they were in the test space or not, or if they weren't, maybe it learned values which are really close to these ones. Another way to compare the results is to see the predictions for values where experiments have never been done. So for higher values of accelerated mass, for example, or quantity of powder. And as you can see here, for the predictions of the chamber pressure and for initial velocity, you have about the same tendencies and the same range of values for both interval predictions and machine learning. So to conclude on this part on experimental conditions predictions, just to remind, the objective was to optimize the trials by predicting experimental conditions or experimental values. And the proposed solution was to use machine learning algorithms to predict the quantities such as initial velocity, the chamber pressure, and the quantity of powder. So here these models have different advantages. First of all, they are coherent to our physical knowledge, which means, for example, we know that for a given accelerated mass, if the quantity of powder increases, then your initial velocity should increase, which is the case with our models here. They give us knowledge on the launcher's limits. For example, we are able to know at which point you reach, at which maximum velocity you will be able to get for a given maximum quantity of powder that you put in the launcher. And they are as precise as interior ballistic softwares. And the advantage that they have on them is that they need much less knowledge compared to interior ballistic softwares, where you need many parameters on the powders, on the launchers, and the projectiles in order to do the predictions, which sometimes you don't have, and you wouldn't be able to do the predictions. So they also have some limitations. For example, you have poor precision for cases with few data. Here we had about 300 samples for the 91 launcher, so it worked quite well. And you have a risk of incoherence as well if you do predictions which are very far from your training data. So to have an overview of this first part, the objective, what we did here was predict quantities which are related to the phase that we call interior ballistics, which correspond to everything that happens inside your launcher. And we saw that machine learning worked well in order to predict these experimental conditions, which are actually directly interpretable results, which means that it is the result that we expect to have. So the objective here was to apply machine learning and artificial intelligence in general to more advanced programs, which correspond to exterior ballistics. And this corresponds to the phase where the projectile is in free flight. So the objective here is to apply machine learning and artificial intelligence to do things that are related to projectile design, aerodynamic characterization, and projectile shaping. And for that purpose, a PhD subject, which is entitled Artificial Intelligence Techniques Applied to Aerodynamics, was launched, which is what I'm working on and which I'm going to present. So in order to do artificial intelligence in general and machine learning, you need to gather a lot of data. And in our case, the data we are working with comes from either simulation, from either semi-empirical tools, or what we call computer-free dynamics. It can come from also the literature, from experiments that have already been done. And it can also come from the experimental data, for example, by launching the projectile with launchers. So once you have your data, we created a database which contains different types of projectiles that we call spin, and drag stabilized projectiles. So just a small factor on this database. So the database contains different geometries of projectiles, which have different aerodynamic characteristics, which are basically what we call aerodynamic coefficients associated to them. The data that we can find in this database are either numerical values, but you could also find images, STL files, or as you can see here, or source files like this source file, which was entered by a tool which is called the PRODAS. And the tools that we use to read this database are called SQL3, which is a database generator. Database Explorer for SQL, which is an interface graphic to explore the database, as well as Python in order to script the writing and reading of the database. So here, once you have created your database, you can do machine learning tasks related to it. And in my purpose of my PhD, there are two tasks that we do with this database. So the first one is aerodynamic predictions for specific projectiles. And the second one is geometry design based on some criteria. First of all, I'll be presenting this first part, which is aerodynamic predictions. So the goal of this first part is to build a function, once again, such functions that will predict what you call aerodynamic coefficients based on the geometry of your projectile and the Mach number, which is basically the speed at which your projectile is flying. So here we have our inputs, which are the geometry of the projectile and the Mach number, and our outputs, which are different aerodynamic coefficients. In order to do that, I used a neural network or a multivariate perceptron. And in our case here, it's a neural network with two hidden layers, both with 128 neurons. So here you have the geometry of your projectile, which is defined with these 5 criteria and the Mach number, and your outputs are your aerodynamic coefficients. So here your neural network with multivariate perceptron can be written with the following equations. So here you have, for example, the outputs of your neurons here, which are based on your input here x and your weights, which are here. Then you have your outputs, the values which are your neuron here n2, which can be written like this, and your global output y, which is here. So here the max value, just in case you are wondering, they are what we call activation functions, which give the non-linear aspect to the neural network. So by training this model, I used the method that is called the backpropagation, which updates the weights sequentially by using a gradient descent. And the score obtained by training it is 0.97, so on a test base. So here I presented it with the coefficient of determination, which is a score on 1, and the more it's close to 1, the better the predictions are, and the further it is, the worse the predictions are. So here, another way to see the results is to compare, for example, the predictions compared to the real values. So here you have a red line, which corresponds to the case where the predictions are excellent. And the more the blue dots are close to the red line, the more the predictions are good. As you can see here, most of the blue dots for these 3 outputs are really close to the red line, which means that the predictions are quite good. But we can have sometimes some outliers, for example, here, here, and here, that didn't get very well predicted. So that was all for aerodynamic predictions. Now let's move on to geometry design. So in order to do the geometry design, you need a flight scenario. And this flight scenario that I chose to present here is the case where you have a launcher which fires a projectile in a straight line at an initial velocity, for example, of Mach 5, which is also the maximum velocity. And you want, for example, your projectile to lose the least speed during its flight in order to reach, for example, an impact at a minimum of Mach 2. So here the design objective is to have a stable geometry with the minimum drag along its trajectory, so from Mach 5 to Mach 2, with the following, for example, geometry constraints on the projectile, which can be, for example, the angle, the position of fins, or the length of fins, and which are also actually my inputs to my neural networks, if you remember. So just a small apartheid on what we call aerodynamic coefficients in order to understand what drag and stability is. So aerodynamic coefficients are coefficients which are associated to the forces and moments of a projectile during its flight. And in our case, the coefficient, right? First of all, CX0, which is called the axial force coefficient, CMQ, which is called the pitch damping coefficient, and CM alpha, which is called the pitch moment coefficient. So in order to have the lowest drag, in our case here, which is for 0 angle for attack, you need to have the lowest CX0 at a given number of Mach. And in order to have stability, you need to have what you call static stability and dynamic stability. And to have both of them, you have to have your CMQ and your CM alpha, which are both inferior to 0. So you also have some knowledge on this coefficient. For example, you know that you have the maximum CX0 is at the lowest Mach number, and your highest CM alpha and CMQ are at the highest Mach number. So by knowing that, you can pose your optimization problem, which corresponds to finding your inputs from x0 to x5 that will minimize your outputs y0, which correspond to the CX0, which is your drag. And in order to do that, we use our neural network that we created before. So the idea here is, for example, to find the geometry configuration that will minimize your y0, for example, from Mach 2 to Mach 5, here I choose to minimize the mean value, but you can use other approaches. For example, you can choose to minimize your CX0 at the point where it is the highest, which means for the lowest Mach number. And you also need your projectile to be stable, which means that you have to have your Y3 and your Y4 to be negative. In this case, I choose them to be inferior to -10 because when it's really close to 0, then your projectile is at the limit of stability, which is not good. So yeah, I added these constraints. And I also choose for them to be negative at Mach 5, which is at the point where your projectile is the least stable, which means if they are inferior to -10 at Mach 5, then they will be inferior to -10 for all other values of Mach. And I also impose that my Y0, which is CX0 here, must be a positive value, which is something that the model should understand, just in case I impose that. And I also have the bounds on my parameters inputs that I showed before. So here you have an optimization problem with constraints. And in order to resolve it, I use a tool which is called the SciPy, which is a library in Python, which offers many optimization tools. And among them is a method called sequentialist squares programming, which is used in order to minimize a function which is subject to constraints. You can see it, for example, as a comparison to MATLAB to BF-milcon. It does approximately the same thing. So here are the bounds that we had on our parameters. And this is the optimal solution that this method gives us. As you can see, all the optimal solutions are within the bound, which is something that we want. And with this solution, you could plot the results for Y3, Y4, Y0 in order to see that if they respect these constraints. For example, for Y3, we wanted it to be inferior to -10 when X is equals to 5, which is also the case here. And for Y4, we wanted it to be inferior to -100 when X is equals to 5, which is the case here. And Y0, you wanted it to be superior to 0 at X is equals to 5, which is also the case here. So this is the main idea behind geometry design, but in reality, it's a bit more complex. You will have many more input parameters on the projectile to predict, and you will also have many more criteria on the coefficients, not just these three, which can make the program a bit more complicated. So that is what I'm working on right now. So another aspect of my PhD subject is based on trajectory generation. So in this first case, we build, for example, static function. Here it will be dynamic functions, which are based on time. And in our case, to build trajectories, which are related to a specific projectile, which is called the basic FINA. And the goal would be to do what we call trajectory shaping, which consists in accomplishing different mission objectives by adjusting parameters, either initial parameters like initial velocity or other parameters during the flight, like activation time and so on. So here is a resume of my PhD. Basically, you have the first phase, which corresponds to gathering the data, a second one, which corresponds to creating a database that will store all the data, and the third phase, which is more machine learning, artificial intelligence in general, to do these three tasks, which are aerodynamic predictions, geometry design, and trajectory shaping. So that is all for my presentation, and if you have any questions, feel free to ask.
Thank you, Alain. Yes, we have 10 minutes for questions. So any question also from the Zoom part? Yeah, Mathieu.
Dans la première partie, tu as comparé les résultats avec un outil qui s'appelait InPal. Oui. Il y a quoi dedans?
Alors, pour moi, c'est un peu une boîte noire, mais c'est censé être basé sur des équations thermodynamiques qui sont mélangées avec quelques essais expérimentaux qui ont déjà été faits pour pouvoir interpoler, je ne sais pas exactement quelle méthode ils utilisent pour voir les résultats.
C'est un modèle musique.
Ouais, c'est ça.
C'est un logiciel de balistique intérieure basé sur les équations d'aérothermodynamique.
C'est Marie.
Ah, bonjour, pardon, c'est Marie Albisser.
C'est un logiciel répandu, c'est fait référence dans le domaine?
Alors, c'est interne à la boîte.
Okay.
Ouais.
On a deux logiciels qui ont été développés en interne justement pour les besoins de quantification, perte de chaleur et choses comme ça. C'est InBal et le deuxième, c'est AMI. C'est basé sur des équations connues, donc le modèle mathématique de la physique de la thermodynamique, quoi.
Les paramètres du modèle sont des paramètres physiques ou ils sont optimisés par ailleurs là, il y a une structure que vous avez choisie, vous optimisez les paramètres dessus ou c'est des paramètres physiques mesurables?
Pardon, vas-y.
Pour les modèles que j'ai construits, pour les modèles.
Non, pour Inbal, pour les logiciels.
Alors peut-être que Marion pourra mieux répondre que moi parce que moi je l'utilise pas tout de suite.
Les paramètres, c'est essentiellement des paramètres physiques. C'est des paramètres de friction, de dimension de canon, de résistance, de propriétés de poudre, dimension de poudre, géométrie, flux de chaleur. Est-ce qu'on considère des ILO, donc des réductions de chambre de canon ou des choses comme ça, quoi. Donc c'est que des paramètres physiques.
D'autres questions? Je crois qu'il est un peu tard. So, Alain, on voulait te remercier pour ta présentation. Bon, last but not least, Taleb fait une petite présentation.